In this video, we are going to see properties of estimators of random variable. Myself, G. Lavanya, Assistant Professor, Department of Mathematics, SRM Institute of Science and Technology, would like to introduce you to properties of estimators of random variables. So, we start with a biased estimator. What is a biased estimator? An estimator of a random variable x is biased if its expected value is equal to the expected value of the random variable that is being estimated. So let me consider x tilde of z equal to g of z. Let my x tilde be an estimator for x. Okay, be an estimator for my random variable capital X. This is biased if we have its expectation E of x tilde of z equal to E of x is not satisfied. Okay, I repeat, it is biased if this condition is not satisfied, where my expectation of x is already known, so that I will be able to check this condition. Next, we talk about an efficient estimator. Suppose we estimate a random variable x from a vector of observations z. Let me say call it for z1, z2, etc. up to zn. Obviously, this is a column vector, so I transpose it. The most important lower bound on the variance for estimating x is given by the Cramer-Rao bound. That is, we would have to find E of x minus x tilde of z the whole squared. This value should be greater than or equal to 1 divided by expectation of, I would have dou ln by dou x of probability of z restricted to x whole squared. This value, if an estimator achieves this lower bound, then it is said to be efficient. Next, the third one is consistency. An estimator is consistent if it converges to the true value of the parameter as our sample size increases. Formally, if I represent theta n cap is a consistent estimator of theta if my limit n tend to infinity, if limit n tend to infinity, probability of mod of theta n cap minus theta should be less than epsilon and should be equal to 1. This should be true for any epsilon which is greater than 0. A consistent estimator becomes arbitrarily close to the true parameter as the sample size increases. Okay, next, we move on to see what is sufficiency. An estimator is sufficient if it captures all the information in the sample that is relevant to the parameter. We say A is a sufficient estimator of B if the conditional distribution of the sample given A does not depend on B. Next, what is asymptotic normality? Asymptotic normality means that as the sample size increases, the distribution of the estimator approaches normal distribution. This allows easy computation of confidence intervals and hypothesis testing in large samples. Okay, the sixth property is mean squared error or MSE. This is a measure that combines both variance and bias. That is, I have my MSE, and if theta cap is the estimator of theta, then my MSE of theta cap is nothing but expectation of theta minus theta cap the whole square. And this is nothing but it will amount to our variance of theta cap plus the bias of theta cap squared. The last property which we want to mention is robustness. Then estimator is said to be robust if it performs well even when the assumption about the population distribution are not fully met, or they are incompletely known, or if there are outliers in the sample. So these seven properties are the key properties of estimators of random variables. Let us now go on to see maybe a few problems based on these properties, or to rather illustrate these properties. All right. Now, let us go on to our first problem. If x1, x2, xn, if x1, x2, etc., xn, let me take it as small letter to distinguish. I write it like this. If small x1, x2, xn is a random sample, is a random sample from a normal population, from a normal population n of mu comma 1, show that show that t equal to 1 by n summation I equals 1 to n xi squared is an unbiased estimator, is an unbiased estimator. Okay, my u looks like a, so is an unbiased estimator of mu squared plus 1. Okay, so when we move on to the solution, first thing is here mean should be known. Obviously, our e of xi is nothing but mu. I variance of xi is equal to 1. How did I get this? I got it because my normal population mentioned was n of mu comma 1, that is mean comma variance, and hence e of xi equal to mu and variance of xi equal to 1 for every I from 1 to n. Okay, now I want e of xi squared. My e of xi squared is nothing but, I know that it is the variance of xi, which I denote as v of xi2. So it is variance of xi plus I will have e of xi the whole square. This I am getting by rearranging the formula of variance, that is variance of x equal to e of x squared minus e of x the whole square. Now this from the data that we have is 1 plus mu squared. Now let me go on to find the expectation of t. What is this? This from the given data is e of 1 by n summation I equal to 1 to n of xi squared. So this is nothing but expectation of, I will have 1 by n. I can rather take the expectation inside the summation. So I will land up with 1 by n summation I equals 1 to n e of xi squared. So this is nothing but 1 by n summation I equals 1 to n of 1 plus mu squared. See, now clearly we know this value mu squared, we can evaluate this value. Therefore, my t is an unbiased estimator. My t is an unbiased estimator. I suppose you have understood the concept of unbiased estimator. We will see one example for biased estimator. Okay, so we'll go to the next problem. If T is an unbiased estimator, if T is an unbiased estimator of, or rather using of, we can say for theta, show that T squared is a biased estimator for theta squared. So this is our question. So how do we go about our solution? All right. So T is an unbiased estimator from the given data. From the given data, what do I have? I have T is an unbiased estimator for my theta. So I have E of t equal to theta. My variance of t is equal to, I will have E of t squared minus E of t the whole squared. So this is nothing but I have E of t squared minus theta squared. So my E of t squared is now turning out to be theta squared plus variance of t. We know that our variance of t is square of the standard deviation, so it can never be negative. Hence, my E of t squared is theta squared plus a positive quantity, and therefore it is not equal to theta squared. Hence, theta squared is a biased estimator, is a biased estimator of theta squared. See, E of t is theta, so it is unbiased. Here E of t squared is not theta squared because it is theta squared plus some positive quantity. Therefore, t squared is a biased estimator of theta squared. I hope now you are clearly able to distinguish and understand between biased estimator and unbiased estimator. We will move on to one more small problem just to illustrate consistent estimator. Okay, so problem number 3, prove that in a sampling from n of mu comma sigma squared That is from a population which is normally distributed with mean mu and variance sigma squared. The sample mean is a consistent estimator. Sample mean is a consistent estimator of mu. Okay, so we move on to our solution. We have to show that it is a consistent estimator of mu. Now, the sample mean x bar, the sample mean x bar, since it is sample, it is small letter, is also normally distributed, is also normally distributed as n of mu comma sigma squared. Therefore, we have E of x bar equal to mu, and my variance of x bar is nothing but sigma squared divided by n. Okay, here it is sample, so it has to be divided by the sample size n. So as n tend to infinity, my variance of x bar will tend to 0 because 1 by n tends to 0, and my E of x bar is undisturbed and its value is still mu. Therefore, let Tn be, let sequence Tn be a sequence of estimators, be a sequence of estimators such that for all theta in our cap theta first subdivision, we have our mean E with respect to theta of Tn will tend to this variance of theta as n tend to infinity, or in this particular case as E theta of Tn, so as theta tend to infinity. Similarly, my variance theta of Tn will tend to 0 as my n tend to infinity. Then we can clearly see that Tn is a consistent estimator, is a consistent estimator of v of theta. Okay, so this is what we want to establish. So I repeat once again, E of Tn tends to variance of v of theta, this value as n tend to infinity, and variance of Tn with respect to theta will tend to 0 as n tend to infinity. How did I get this? My variance is having 1 by n sigma squared as n tend to infinity, 1 by n tend to 0. Similarly, when I come over here, I have to just check for the mean. When I check for the mean, please look here. My mean is given by this value mu. Since mean is given by mu, I will have no other value. E of x will tend to variance of theta as n tend to infinity. How did I get this value? I got this by rearranging the terms. Okay, thank you.